So you have 900 millimeters of liquid water in the snowpack, the very high amounts here. And you compare it to the 2-kilometer simulation, you can see blues in greens, nicely correlating here. This pattern is nicely correlated here as well. So you can see at the high resolution, the model is actually able to get within 5% the actual snowfall. So this is really a great result. We did not anticipate that we would be able to do so well. In fact, my National Science Foundation sponsor actually didn't believe me the first time. I'm not sure if he does yet, but I think I've finally convinced him. If you look at 36 kilometers, you can see the resolution smooths out the snowfall significantly. So yellow is 500 millimeters. So we're getting half of the snowfall that you would with the high-resolution model. And of course, this has great impacts for hydrology. This snow, because it's at high elevation, will last a lot longer than this snow because this is at much lower elevations, it's much warmer. It will melt very quickly. And it's half the amount as well. So if we compare, we did 4 different years at 2-kilometer resolution. And the blue line is the WRF model, and the red line is the SNOWTEL. And you can see we're within 5 to 10% in all cases. So we feel like that this is a very good resolution. And just to look at it on a monthly basis, we'll take 1 year, November 2007. On the left is 2-kilometer. In the middle is the SNOWTEL, the dots. And this is the difference plot over here. And then this is the mean over that month right here. So in November, you can see we agree quite well. December, you can see it's capturing all the events quite well within the standard deviation, the gray shading. January, same, maybe a little bit high, but not bad. February, still good. March, April, we're a little bit low. This may be due to some issues with convective parameterization, but if you go to June, the same year, you can see that we do a really quite good job with convection in the summertime. And the reason I show this is because this is what you're going to have to look at in terms of Thailand in doing convection. You have elevated terrain, and so the elevated terrain drives the convection. Those are the preferred spots for thunderstorms. And you can see when you do have the terrain, it tends to focus the thunderstorms at particular locations. And this type of model with 4 kilometers or 2-kilometer resolution can do a very good job in capturing the convection. So this is very important. Here's August, same thing. We're capturing the patterns. You can see in this case we have much more widespread precipitation compared to the SNOWTEL. But again, the model's doing a very good job, certainly within the observations. So this is exciting because now we can start using these kind of high-res models to do some really good physical process studies in places like Thailand and other countries. Israel is starting to do this type of work as well. We also compared 2 kilometers to 4 kilometer simulation, and you can see for this particular year it agrees quite well. This is November 1st to November 1st. So in the next part, I wanted to just talk a little bit about the model grid resolution. And I'm going to skip over this plot and just go to this plot right here. So what we did is we compared a 4-kilometer simulation to a 12-kilometer simulation to a 36-kilometer simulation. So when we're running at 12 kilometers, we have to use a convective parameterization, and at 36 kilometers. This is for 1 year, average over an 8-year simulation series that we did. And at 4 kilometers, you see both in the winter time and in the summer, we get good comparison to the SNOWTEL data. But at 12 kilometers, we underestimate in the winter time slightly, but we overestimate in the summertime. And that's due to the inadequate representation of the convection by the convective parameterization. At 36 kilometers, it's worse. You get a significant undercatch in the wintertime and the same type of overcatch in the summertime. So this is compensating errors. So you undercatch in the winter, overcatch in the summer, so you think, oh, I'm not too bad. But you get the seasonal cycle completely wrong. So it's very important that you capture the seasonal cycle. So what do you gain by doing high-resolution simulations? Well, what you gain is you capture the vertical motion much more accurately. And that's what's driving a lot of precipitation in complex terrain regions, such as in Colorado or northern Thailand. The vertical motion here from a cross-section on one particular day from the southwest to northeast is indicated here, and the red colors are in the order of meters per second. So we're getting 1 meter per second updrafts, and that's driving the microphysics to produce precipitation at these locations. If you look at 36 kilometers, the updraft is much weaker, only 20 centimeters per second, so factors of 5 less. The terrain is also much smoother. So the driving force for precipitation is the vertical motion, and that is well captured when you get down to these high resolutions. So what's the difference with the 36 kilometer versus the 2 kilometer? Well, this is a map, a movie of snowpack starting in December. We're now in January 18th. This is 36 kilometers. This is at 2 kilometers. This is now end of February. So as I mentioned to you, in Colorado, a lot of the snow melts in April. So you can see here the blockiness of the 36 kilometer snowpack and how we resolved the snowpack quite nicely in the 2 kilometer. Now we're coming to the end of March. Now we're starting to get melting over here. A lot of the snow is disappearing. This is now the end of April, and by the end of April, it's gone. Whereas in the 2 kilometer, we still have 2 more months of snowpack remaining. So again, if you're trying to do a dynamic statistical downscaling, if you have no precipitation or no snowpack, you really can't do a very good job of statistical downscaling. So we've done an 8-year simulation, continuous simulation. So based on those results, we were confident that we could do this. We extended it so we can do the summertime and also to do a better job on the soil moisture spin-up issues. This is comparison from 2000 to 2008 at the SNOTEL sites, and you can see a very good comparison in the precipitation, and this is the snow water equivalent from the snowpack, and we do a pretty good job on that. We're not quite getting the peaks, but not too bad. So that's the current climate, and then we did this pseudo-global warming simulation to study the impact of an increased temperature and moisture on the headwaters water cycle. So we give a perturbation of 2 degrees Celsius and a moisture of 15%. So how do we do that? Well, we look at the NCAR CCSM 50-year A1B simulation, and we give a perturbation based on this to the North American reanalysis, and then we use that to drive the WRF model. As I mentioned, this is all described in this paper here, and it's based on this work that Chris Shar pioneered in 1996. So we calculate the perturbation in the 10-year monthly mean of the UV temperature, geopotential height, and water vapor mixing ratio between the current and future climate periods from the global climate model. So we have these monthly means. And then we formed the perturbation. So that's the difference between 1995, 2005, and 2045, 2055. And then we add that to the North American reanalysis boundary conditions. So this is the current reanalysis, and then we add this perturbation. So that's our climate perturbation, climate change perturbation. So what we have to note, though, is that sub-monthly phenomena such as extratropical cyclones are not really captured except for the mean effect. So this really is looking at the same type of storms in the future, but with the temperature and moisture perturbation. And this is what it looks like in terms of the perturbation. We're getting additional temperature. This is the warmer temperature, about 2 degrees C, over a vertical cross-section through the mountains. And this is the increase in moisture. You can see about 1 gram per kilogram increase in moisture, about 10 to 15%. So that's more or less what we expect. So then finally, I'd like to look at the impact of warming over the water cycle over the headwaters. So what we're going to do is over that Colorado headwaters subdomain region, we're going to look at these 3 terms: runoff, Q, precipitation, and evapotranspiration. On an annual basis, neglecting soil storage, we can form this equation. So the runoff is equal to precipitation minus evapotranspiration. Or the delta Q is equal to delta precip minus delta ET in terms of climate change. So these three terms are what I'm going to look at. So I can then form a ratio. I can do a little bit of math, and then you can form these ratios. So we have this ET over P, which is sort of the evaporation efficiency, and Q over P is the runoff efficiency. So the question is, over Colorado, over Thailand, what fraction of P is ET, and what fraction is Q? So think about that. How much of your precipitation is evaporated in Colorado? All right, so put that into your head, and we'll come back to it. What I'm going to show in the future, in the next few slides, is I'm going to look at the average over this subdomain. We have details like this. This is winter precipitation, summer precipitation. You can see it's less. And this is the annual. And we're going to look at differences of this in the future. So that's future. You can't quite see any differences here, but if you look at the difference field between future minus current, this is difference in the winter. This is difference in the summer. So in the winter, you get more precipitation. In the summer, you get less. So this was a surprising result. If I have time, I'll talk about this at the end of my talk. So now I'm going to show you a series of slides where we subtract the future minus current precipitation over the domain. So this is average over the domain, and this is over an annual cycle. So we're starting from October and going through October here. So what happens to precipitation? Future minus current. So precipitation increases in increases in the wintertime and decreases in the summer. But the net effect is a positive precipitation. What happens to rain? Well, more of the snow is actually converting to rain. So we're getting more rain in the winter, a little bit less in the summer. What about snow? Snow is interesting. We start off with a little bit less, but then because of the moisture environment, we're actually getting more snow in the winter in the future than we were in the past. And then it decreases here. Snow cover, because of the warmer climate, we actually decrease snow cover. So by April 1st, we're 15% less snow cover. I'm going to skip that slide. This is the snow-water equivalent difference. And this is now the snowpack. So you can see the snowpack actually doesn't change that much, which is good news. But it does eventually start decreasing because of the increased melting as we're getting warmer. ET does increase, as you might expect. It rapidly increases in March, April, May. And then the runoff is the final answer. So what happens here is that because of the warmer environment, our runoff is earlier. So we get a peak early on in March, April, May, and then it rapidly decreases as we get the evapotranspiration kicking in. So we actually get a negative, slightly negative runoff. And soil moisture increases. So in terms of seasonal variations, I think I've described these already, so I'll skip the slides. But I do want to mention changes in seasonality. Snowmelt starts 2 weeks earlier in the future and ends 3 weeks earlier. And the early end of snowmelt reduces runoff significantly in June, as well as the period for evaporation. So again, large impacts of warming, and I think I've already talked about this as well. Snowfall increases due to the moisture storms, and we get less snow cover. So going back to this equation, this is the question I asked you before. What fraction do you think the evaporation is compared to precipitation over Colorado? Anybody have any ideas? Anybody want to guess? This is the audience participation part of the talk. How many vote for 50%? No? Nobody's willing to stick their hand up. How about 80%? Okay, one person for 80%. Okay, the answer is 80%. So evaporation is huge. Okay, this is really important to get evaporation right. Current is 81%, and the runoff is only 19%. In the future, it's even worse. We get 83% evaporation and only 17% runoff. So you have to get both the precip and evaporation right in order to do this global water cycle. If you look at the global, remember we started out